Let's talk about how cool and practical and useful these conic sections are. The circle, of course, we've known about circles for much of our lives. It's a conic section. If you slice a cone parallel to its base, you get a perfect circle. And of course, we know that a circle is the set of all points equidistant from one central point. It's a locus of points. We sometimes use the word locus. All the points that are exactly the same distance from a central point. If I rotate a circle about a line, I get a sphere. And spheres are incredibly useful in all sorts of ways. One use is in optics. We use slices of spheres in lots of different optical applications. Here's one example. A Fresnel lamp uses slices of spheres to help aim light. Very cool. Let's look at ellipses. And let me just say, a circle is actually an ellipse, just as a square is a rectangle. So an ellipse is a slice of a cone. If the slice is perfectly parallel to the base, we call that ellipse a circle. If the slice is not, then it's just an ellipse. Right? So you may have done this in earth science. Each one of those green points is called a focus point. And if you stretch a string, right? If you have two nails and you create a string and you stretch that string with a pen or a pencil and draw a curve, you'll end up with a perfect ellipse. In other words, that D1 plus D2 is always the same. That's the locus of points that creates an ellipse. I think we all know that we orbit the sun in an elliptical pattern. Pretty cool. They have amazing reflective properties. So if I put a source of light on one focus, all those light rays will bounce and reflect and hit exactly the other focus. So let's see how that works. If we rotate an ellipse around an axis, we get something called an ellipsoid. And if you slice that ellipsoid in half, it becomes a spotlight. See how that works? So here's an ellipsoid sliced in half. The light source is at one of the focuses. Everything reflects in such a way that it has a pinpoint beam at the actor. And it does the same thing with sound. Have any of you been in a whisper room? Grand Central Station has a whisper room. One person stands at one focus and they whisper and all the sound bounces. And if someone's standing at the other focus, it's as though that person is right there whispering in their ear. Very cool. And here is our parabola. We've been learning about parabolas forever, but we haven't learned about them in this context. They are also slices of a cone. If you slice a cone parallel to the side of the cone, you get an exact parabola, which could be described by a quadratic function. In terms of locus of points, I think you may have learned this in Algebra 2. If we call the green dot the focus, so the ellipsoid, the ellipse had two foci. Parabola has one focus. And the distance between each point and a line called the directrix is the same as the distance between that point and the focus. You learned this in Algebra 2, I believe. All right, we see this in astronomy. Many comets. We just had a comet visiting us recently. Many comets shoot through our solar system along a parabolic path. And parabolas are used in satellite dishes. So again, if we're rotating a parabola, and getting a three-dimensional thing, they make great receivers, and you can see why. If rays are coming in, the way that the parabola is shaped, it bounces every single received wave and bounces it straight to the focus. And then you would have your receiver. So these are used for satellite dishes and for mirrors for telescopes. And they're used in floodlights as well for that same reason. The light would just be going in the opposite direction. You'd have the light here at the focus, and then all the light would bounce off and go out as a beam. So let's look at a hyperbola. A hyperbola relies on us using what we would call a true mathematical cone. We often refer to a cone as just like 1/2 of this, but actually a cone, technically in math, is this. It's made up of what we would think of 2 cones. And if you slice this cone, you get a hyperbola. And believe it or not, this looks like it's being sliced straight up and down, but you can also slice it on an angle and still get a hyperbola. And a hyperbola also can be defined as a locus of points. It's kind of like an ellipse in that it has 2 focus points. But in an ellipse, your string was, your D1 plus D2 is always the same. Now the difference, D1 minus D2, is always the same. Super cool stuff with hyperbolas. You can create one, at least half of one, by just setting a flashlight down on a surface, and you'll create part of a hyperbola. It explains why we hear sonic booms. Ooh, if you have a jet or a plane that's going faster than the speed of sound. We've all, I think, experienced the sonic boom, right? It has to do with the change in air pressure that the jet is creating. And the sound kind of creates a cone shape. And when that cone intersects the earth, it intersects it on that kind of hyperbolic path. And that's where we hear that boom can be heard and felt along the red edge of the hyperbola. Right? Nuclear power plants, those cooling towers are actually shaped in the shape of a hyperbola. It's the most efficient shape for cooling. But it also has a cool reflective property that is used in different lights. So look at this for a moment. If you have just one part of the hyperbola and the light source right there, the light bounces and you get more of a diffuse light. And if you trace all of those rays back, they seem to originate, if you will, from the other focus. Math is the coolest thing in the world. Come on, admit it.
Yesterday, a child came out to wonder